Redshift. What do we mean by redshift? Well, to understand redshift, we have to take a look at how light travels. Okay? Many of us have been to a beach or seen pictures of a beach or the ocean, and we know that waves travel through the ocean. And if we were to look at a wave, we could measure a couple of different things. And the thing that we are interested in is the distance from one wave to another. So if we were watching the waves come in, the distance from the peak of one wave to the peak of the next wave behind it is what we're interested in. We call this our wavelength. Okay? And so this is how the energy travels through our medium as a wave. But the distance between them is a wavelength. Well, light also travels as waves through space. And so they have a wavelength in space as well. Okay, and so if we look at and we measure our light as it goes through space, we have a peak from one wave to the peak of the next wave. The difference between a wavelength in the ocean and light wave in space is size. Light waves are extremely tiny. So now every color of light has its own wavelength. So if I had, for example, blue light, they have the shortest wavelength. And red light has the largest in terms of color. Now, redshift looks at how objects moving away from us. So an object or a star far away from us releases its light, and that light has a wavelength. But as the universe expands, it causes this wavelength to be stretched. And so now, although this was the wavelength of light that was emitted from the star, that wavelength gets stretched and it's now become longer. And since it's become longer due to the object moving that produced the light moving away from us, it's become redder. Okay, and this is what we call redshift. So now for your note, because of the redshift, the increase in wavelength of light, this allowed us to determine that objects that are moving in space are moving away from us outside of our galaxy. Okay, within galaxies, the distance between things remain constant, but between galaxies, so if I measure the distance from our galaxy and another galaxy, the distance between them is expanding. And in fact, what we find is that the further an object is away from us, the greater the redshift. So this was what Hubble discovered that allowed them to make his predictions in terms of the expansion. Now, this value is extremely important because it's one of the ways that we measure the age of the solar system. Now, our third piece of evidence or pillar is our abundance of light elements. Okay, and so our light elements being mainly hydrogen and helium, and the fact that the universe is composed mainly of these two elements. They make up the large percentage, okay? And this is because after the Big Bang, we had just energy, and then when that energy formed into matter, we formed mainly hydrogen and some helium, okay? And if we look at the ratios of hydrogen and helium to the other elements, it follows exactly what we would expect. Okay, so here's your note. Okay, we have mainly light hydrogen and helium. We have only a small amount of our heavier elements. And if we look at objects that are really far away from us, because the further away something is, the deeper back in time we look at it, we find more and more hydrogen and helium and fewer of our heavier elements. Okay. When the Big Bang occurred, it produced a large amount of energy and radiation. But as the universe expanded, this energy was stretched and it cooled. And so it caused it to shift from really high energy waves to much larger waves that have less energy. And so just like we had our redshift where it expanded our visible light from being blue to say more red, or from red to even more red, we can also have this occur with the residual energy of the Big Bang. It's been stretched so much that it is now in the form of microwave radiation. Okay? And if we take a picture of the night sky and we measure our background cosmic radiation, what we can see is we can see an image of the night sky where we have regions where it's really cooled and regions where it's warmer. And this is what we would expect to see if the Big Bang Theory was correct. Okay, so here's your note. It was originally really hot. Some of the leftover heat, when it expanded, it went through our other forms of energy because of our electromagnetic spectrum until we're left with microwave energy. And this forms our cosmic microwave background radiation. Okay, and this was detected by 2 researchers, and they were rewarded with it for finding evidence in terms of a Nobel Prize, I think. One of the pieces of evidence for the Big Bang Theory is its age. And we get its age in 2 ways. One, we can look at the oldest things that we can find, and second, we can look at the rate of expansion. Okay. So the first thing we can do is we can look at globular clusters. Now, a globular cluster looks at galaxies and the things around them. We like to think that a galaxy is nice and neat, right? And so our Milky Way galaxy, it's relatively flat in terms of its diameter, right? It's only about 1,000 light years or 10,000 light years in diameter, but it's much wider. Okay, so its thickness is small compared to its diameter. However, around that are other microgalaxies and other things that feed into it. In fact, you could think of a galaxy much like a large city, where the large city has most of the information, but in suburbs around it, we have other things that feed into the galaxy. Same thing happens with globular clusters. And so if we look at them, what we can see is that our universe is somewhere between 11 and 18 billion years. Okay, now, why do you say so big? And then you say, wait, 18 billion years is older than what we're saying the universe is. This allows us to put a lower limit on the age of the universe. Plus, there is error in our measuring and some of the other assumptions, so it makes it hard for us to narrow down this value. But one of the key things we also know is we can't have stars older than the universe it is. And so our oldest stars put the universe around 11 million years. Okay, so we can see here an image of a globular cluster, right? So here we have our galaxy and we have all kinds of features around it. So another way that we can determine the age of the universe is by looking at the rate of expansion, which we call our Hubble constant. And our Hubble constant measures the expansion rate, which is right now 70 kilometers per second per megaparsec. And this allows us to come up with how big the universe is getting. And it has a much narrower uncertainty, and so this allows us to place an upper limit on the age of the universe. And so it puts it between 12 and 14 billion years. So when we combine these two things together, the oldest features that we can find are the information from our globular clusters and also our Hubble constant. That's what gives us our 13.8 billion years. Okay. So now you can fill in your note on the age of stars. Okay, if we look at the evolution of galaxies, okay, we have our Big Bang, then we have about 1 billion years after we start to have our first galaxies, we have our galaxies occur, and we have our different types of galaxies, and ultimately we end up with a hierarchy. And if we look, we have, if we look at our oldest galaxies, so we look really far back into the night sky, our galaxies are spread out, they're mushy, they don't have a defined structure because they didn't have time to get into their structure. Whereas if we look at galaxies that are closer to us, which are not so far back in time, what we see is we see galaxies with a nice defined shape. And so this nice defined shape is what allows us to understand the structure of the galaxy, and the fact that they've had time to go from messy and to organization. Okay. So basically, if we look back, we should see small irregular ones, and nowadays we see closer to us, we see more structured.